In this part we focus on the dimensional analysis. What is dimensional analysis? Dimensional analysis is a powerful tool to check that all the physically related measurements are correct and compatible. So we check the units of various physical quantities and we perform rigorous analysis of a formula which apparently describes a phenomenon to verify if the formula makes sense, if it has a physical, concrete meaning. What are the fundamental quantities that we have? We have time, we have mass. So in order to carry the dimensional analysis, for t we use capital T inside brackets. For m, which is the mass, we use capital M inside brackets. And for the distance, which is length, we use capital L inside the brackets. Here, these are fundamental quantities because Isaac Newton, we know that he formulated the laws of mechanics and kinematics, and he explicitly described motions of a moving object. From his work, his celebrated work is this one, Principia Mathematica Universalis. Now let's go and have a look at the most fundamental quantities, which is the velocity. Let's carry out the dimensional analysis. We will use the bracket here, v equals bracket x, and here bracket t. That is length, and the denominator t is time. So here can be written as L t minus 1, which is meter per second if we want to use the SI system, International System of Measurements. For the acceleration we use bracket v, bracket t. So the bracket v is L over t, and here in the denominator we have capital T, so it should be L times t minus 2. So as we know, the acceleration is meter per second squared. This is what it means. So let's go to the first example. We have a linear motion with constant speed. So we have this equation here, and we want to carry out dimensional analysis. X naught is the initial position, v is the velocity in meter per second, t is time, and we want to check that this formula is physically correct. Let's see. Bracket x equals bracket x naught plus bracket v bracket t. What is x naught? Is the initial position, so it's a distance L, capital L, plus the dimensions of the speed are the following: is L over capital T times capital T. So here we can treat this as normal numbers. We can simplify, and we have length, and here we have length. So the final result will be length in meters, for example. This means that my formula is mathematically and physically correct. So it's not it's representing a real phenomenon, and it's not something out of the unreachable. So this is true. This formula is true. Now let's go to the second problem. We have a pendulum, and the period of oscillation of a pendulum is given by this formula, 2 times pi square root of the length divided by g. The acceleration of gravity is g, and L is the length of the pendulum. T should be time. So let's carry out t equals bracket 2 pi times this is square root. Here we have L, and here we have g. So it's 2 times pi square root. L is of course distance with capital L, and the acceleration is L over t squared. Of course, we don't care about the 2 pi because it's just a dimensionless quantity. Here, this one is dimensionless quantity. Okay, now let's work this out. Let's simplify this. This is t squared over L. So we can cancel the L's and we have 2 times pi bracket t. So the t, the SI is in seconds. So the formula here, it makes a physical meaning because the oscillation depends on the length. So if you can decrease the distance from the wall of the pendulum, the acceleration of gravity, of course, you have the weight that drags the weight down, the acceleration of gravity. So the period of oscillation would depend on the L and G. And this is verified because see here we get that the period is in seconds. If we have gotten something else, then obviously the formula is not correct. Now let's have a look at this one. You have an object with mass m traveling through a cliff. Here you have the distance h is this distance here. So you have the gravitational potential gravitational energy, dynamical energy, and this is the kinetic energy. So when it moves down the cliff, it has a speed, so it has a kinetic energy. Let's carry out dimensional analysis. We have a half bracket m v squared plus m g h. It's a half times capital M, and here we have L, distance divided by time, and of course this goes squared, plus the mass m times L over t squared times L. That's a half times m L squared t squared plus m L squared t squared. So the dimensions of A is m L squared t squared, or kilograms times meter squared over second squared. SI system. So the formula makes physical sense. We have the mass, the speed, the acceleration of gravity, and h. These parameters determine the total energy in this case. Okay, the volume of a cone is a third times pi times r squared times h. Let's check the dimensions. Of course, this is just a constant. We have r times h in brackets, a third times pi. This is L times L times L. This is L cubed. So the dimensions is L times L times L, L cubed, so it's cubic meters, which makes sense. So the SI measurement is in cubic meters here. Let's have a look at problem 5. The density is given as the quotient of mass divided by the volume. Is rho equals brackets m over v. So it's capital M over L cubed. It's kilograms per cubic meter. Let's go to problem 6. We have the radial speed and radial acceleration given by this formula. Omega is the angular frequency. Omega equals 2 pi over period t. So let's carry out dimensional analysis, brackets, omega r. So it's 2 pi 1 over bracket t times distance L. So it's 2 pi L t. So this is meter per second in SI. Okay, the dimensions are these ones for V. L over T, meter per second. Let's do the same for the acceleration. Is omega times r. The dimensions of omega are 1 over t times 1 over t times L, so it's L over t squared, so it's meter per second square. The radial speed, okay, depends on the angular frequency and the radius of this disk here, and the radial acceleration depends on the square of the angular frequency squared times the radius. So this couple of examples, we have checked this couple of examples doing dimensional analysis, and we have verified using this powerful tool that the formulas that we all know and we go across the engineering and applied sciences, that these formulas are meaningful and they represent some physical quantity. Otherwise, if we don't have this tool, then we don't know if the formulas that we get are correct.